All right, welcome to Lab 10. Lab 10 is going to be an introduction to C++, and it's going to sort of wrap up a lot of the ideas that we've been looking at throughout the course in Compute 127. In particular, we're going to extend this notion of types that we first saw for things like scalars, like integers, or floating point variables, and then we extended them to structures, which combined various scalar types together to give you a single struct that can be manipulated together. And now we're going to combine the data and the functions together into a new type called a class, and it'll enable us to encapsulate an object in one place. So all of the data and the functions that act on the data will be declared in one place. Let's start with a very simple example of C++ code. As you can see, this looks very similar to the C code you've been writing. The main difference is here on this line 14 of this file. You can see that I've declared a image variable. This variable img is the variable I'm going to use, and as you can see, it looks like a function call because it has open round brackets and closed round brackets here, and it's giving a argument here. In this case, it's the file name, which is consists of the image file that we want to load. And notice that its type is given as capital I image, so it's a new type. It looks somewhat similar to a struct, but in a struct we would be allocating it or doing an image create function, and that returns a pointer to an image. But instead, this is just an image type, and we seem to be calling. So what's happening here is that image here, this highlighted three-letter identifier img, is actually going to be the variable which is of type image, right? So just like we declared something of type integer or something of type double, this image is of type capital I image, and is defined somewhere else. So it's defined in this image.hpp file. So let's take a look at that next. So here I've loaded up in my editor the file image.hpp, which was hash included by the main function we just saw, or the main C file, which has the main function. And in this case, you can see that what I've done to define this type, which is capital I image, is to define it as a class, and then it has an open bracket, and this open bracket defines all of the things about this type image that we want to say about this type. So it's going to contain data. So they can be either data can be public or private. For the sake of this demo, I'm just going to use public. In practice, you might want to keep the variables hidden if you don't want people, sort of the users of your class, to modify these variables without going through the functions defined in the class. Then you might want to define them as private. So for example, if you don't want something that just uses your image class to be able to directly modify columns and rows, but instead you want it to use like a resize function only in order to resize it, then you can make these two lines inside something called private, which looks exactly like this. Instead of public colon, it would be private colon. But for all of these demos, I'm going to always use them as public, and they're going to be public in your Lab 10 as well, just to make it easier for us to auto-grade your submissions. And so here I've defined a pointer to pointer type for a 2D array. So basically it's going to consist of an actual two-dimensional matrix that contains all the pixels. And this is this kind of part of your Lab 10. So this class, you need to allocate this memory, and it's going to have, you know, these many columns, and each these many rows. Each of the rows will have certain number of columns allocated for it. So the first thing to notice is that C++ adds a whole lot of stuff to C that makes it convenient to encapsulate information about this new type you're defining called image. So the first thing is we're going to have functions that have no return types. So any function without return type is and it has the same name as a class name. So in this case, it has no return type and it has the same name. So image, same as the name of the class, and it basically is what's called a constructor function. A constructor function gives you a new instance of this class. That's called an object. So it's the same as having a type, like a struct type, and then when you actually malloc it, it becomes allocated in memory and you can use that struct. In the same way, you can define a class. It's like a type, and it has data like columns, the number of rows, all the pixel information. That's the data. It also has functions like this constructor. And when you call this constructor, it actually creates an object that is allocated in memory for you. You can have more than one constructor. So in this case, there's a constructor image, again the same name as the name of the class, and it constructs an image of a certain width and a height, and it fills it with some color. So notice that the color here is assumed to be a uint8 type, so it's going from 0 to 255. And then you have another constructor which takes a file name. So this is, if you remember, the one that we used in the main function that was calling, using this header file to create an image, was using this constructor. It was passing it a file name. It can also have a copy constructor. So this constructor takes another image and makes a copy of it, and you get a new copy of that image. And it should be a deep copy. It means that they shouldn't share the same pixel array, right? So it has to make a whole copy of the pixel array, which is an entire duplicate of the a.pixels allocated array. And so these are all the constructors. You can also define a destructor. The destructor is typically just one of them because you don't need more than one. It takes no arguments, and then what it does, it frees all the memory allocated for the image. So it, for example, should free all the memory allocated for the pixels and so on. And then you can have a bunch of functions defined. So notice they're still all inside the curly braces of the class image definition. And there's a function called resize, setPixel, getPixel, all the stuff you're familiar with. And then there's a few other functions like show, and then a function called drawLine. So all of these are inside this. So if I go and look at the matching brace, so that's a matching brace for class image, and then there's a semicolon to fill it out. So the question is, where do these functions exist? So none of these functions are defined here, but that's the same as what we had before, right? So this is just a header file. A header file just contains which functions exist or which types exist. The actual implementations are defined somewhere else. So that we'll look at the file image.cpp next to look at the way that all of these functions are defined. Okay, so this is what image.cpp looks like. Notice that we have hash included image.hpp, which contains the definition. And now we want to, so this syntax here says, I'm trying to give you a function that belongs to this class, and it's the class is defined somewhere else. In our case, it's in the header file which is included, and this double colon, and then there's a function name. And in this case, it's a function that defines a constructor, And then right after the parameter list, C++ has this extra syntax which has a colon, and then it has a bunch of variable names, and these variables are the variables defined in the class. So inside the image class, there was columns, rows, and pixels. And what this does is gives an initial value. So it says the columns are 0, the rows are 0, the pixels are 0. And in this case, it didn't save that much typing, because we could have just written down inside the body of this function, we could have written down columns equals 0, rows equals 0, pixels equals 0. It would have accomplished exactly the same thing. But in some cases, it might save you some typing to initialize the variables like this. So this first constructor is very simple. All it does is says I'm getting an empty image, right? So I just constructed an empty image. It has 0 rows, 0 columns, and pixels are assigned to null or 0. This is a more interesting constructor. It takes a file name, and then it calls a function. In fact, it's preferable to call a function rather than copying what this function does back into the constructor. So this is a function that is actually defined in the class. So you don't have to use image : again, because it's part of the image class. So this function was defined inside it. And it takes a file name and loads it up, and what will happen is the columns will be set to the right values. Initially they're set to zeros. After we execute this load function, the columns, rows, and pixels will be set to the size of the file, right? The image in the file. The other constructor we have here takes a actual the number of columns, so the width, the number of rows, the height, and then the fill color. And here we could have used, it's again setting it to 0, but because you cannot do an allocation in this, you can only set it to some value. So instead we're going to call the resize function. The resize function actually will create the pixel array of the right size, with the right number of columns and the right number of rows, and so on. And finally we have the destructor, which destroys the image, essentially frees all of the memory associated with that object. And it says if there is pixels, then we delete the pixels, and it uses this representation in order to recursively call delete on all of the elements of pixels. So it assumes it's an array, and then it calls delete on those array elements. You could also go and delete each allocated element of pixels by using delete one by one. And then, so that these are all functions that were either, so they were, this is a constructor and a destructor. They didn't have any return types. This one has a return type of void, which is a resize function. Again, we have the class name : and then resize is the name of the function. Takes 3 arguments: columns, rows, fill color. And then if the pixels exist, we delete it. So C++ actually doesn't make it easy. It's not natural to use realloc, although you could use realloc. It doesn't make it natural to use realloc. So instead we just delete it and we allocate a new 2D array. So this is another operator introduced by C++. Instead of malloc, we use an operator called new, and new takes a type and creates an allocation for that type. So in this case, we are going to create an allocation of an array with the number of rows, and each element is going to be uint8t pointer, because we're going to allocate the for each row, we're going to allocate the number of columns for that row. So pixels I is equal to new again, and the number of columns. So as you can see, this is creating a 2-dimensional array, and the nice thing about it is you can use just a standard matrix notation, although it's slightly different from the math matrix notation in that it has an open close square bracket and then an open close square bracket, but it's close enough to the math notation that people like it. So it says pixel ij, for each pixel ij I'm going to assign it a fill color, right? So we can use sort of standard matrix notation to manipulate this two-dimensional array. And I seem to have introduced a typo here, so I'll just save that. And that's it. So we just now assign the value of columns to the new columns and rows to the new column, to the new rows, sorry. And this pointer is referring to the current object that's of image type. So this pointer is a way to refer to the variables that are part of the object. And then this columns refers to the parameter name that was passed to this function. So if, for example, this was a totally different variable name, you could have just omitted this pointer and it would have worked. So if this was called, I don't know, C, then I could have said columns equals C and it would have worked because it knows that columns is a variable inside the image class. But now there's an ambiguity, so I make it explicit by using this pointer. You don't necessarily have to use this pointer. Some people say you should use it all the time to make things clear, and some people say if it's inferable, then don't use this pointer. It does definitely save a little bit of typing to not have to type in this pointer every single time. So I tend not to do it, but other programmers that I respect say you should do this pointer all the time. Let's go back to the main function and just look at how it was called again. So we defined a new variable image, which is using the constructor function and creates an object of this type, which is class image, right? So it creates a new image, and this constructor is using a file name to load it from a file. And then the first thing it does is it shows the image, and then it draws two lines on the image. So one line and another line, and both lines are white in this case. So as you can see that implicitly this image is an image that can only create these grayscale images. So the color, every pixel has a color. That color can only be from 0 to 255, and the reason for that is, if you look at the header file, the reason for that is this declaration inside the class, right? So it only has the ability to store pixels that have a value between 0 and 255 because that's what a uint8 type does. So if you go back to the main function, this image can only be a grayscale image. And so what we'll look at next is to see how we can make the implementation of an image not so dependent on the color of the pixels or the type of the color of the pixels. Maybe we want to store, load, resize, and do all these functions that we've defined, and we don't want to do this just on grayscale images but on color images, or maybe even if you have red, green, and blue values plus transparency, then we still want to think of that as an image. So how can we take the same functions and ask and create a class that would not just work for grayscale images like we've done here, but also work on colored images or images of different color types. So we'll just look at that problem next and see how to solve that using C++. So now we want to ask the question, what happens if we want to define an image that has a different pixel type? So we don't want to represent a pixel with a grayscale value from 0 to 255, but maybe we want to represent that not with a uint8, but maybe a double. Or it could even be more complex than that, and it could be 3 values or 4 values. So we want to abstract away from how the pixels are represented, but we still want the class to actually know about the fact that image has columns and rows, and it should do the same things like resize the image or create an image. Most of that doesn't really depend on the pixel type. It only depends on the fact that you have a two-dimensional array, right? So a lot of the algorithms you do on images iterate through the two-dimensional array or single-dimensional array, depending on how you represent the pixels. And so we want to say that those algorithms should remain, but it should work on different pixel types. And this is what this syntax is letting us do. So if you notice here, this is a capital T, and this variable pixels, which is an element of this class image, is very similar to the one before, where it was a uint8 type, and there was a pointer to the number of so basically an array of the rows, and for each of the rows there was an array of columns. So this was defining a two-dimensional array of pixels. And instead of having a specific type of the pixel, we're going to say that it has a generic type. So it has just a type capital T. And in this particular syntax, you have to say that it's a template, and then you have these left angle bracket, right angle bracket, and it says that it's a type name of type T, right? So you can use type name, you can use class. I prefer type name just because it says that this T is to be type checked as a kind of type. So C++ will, if you give it a number, for example, it will say, hey, this is not a type, so you can't use this as a template variable. So in this case, C++ says, oh, I see that this is a template. I'm going to take an image of, when I create an image, as you will see, it has a syntax to say I want an image of a certain pixel type. When I give it that type, it's going to create a specific image class of that type. So it just creates a new class for every type you want. But it only does that if you need it. Like, it doesn't create a class for every possible type, because there are infinitely many of them, right? So what it does is, when you need an image of a certain pixel type, it will create one for you, and will create a specific implementation of that with that type. So if I wanted to use this in a constructor, the way that I would use it is in this manner. So I would load up an image in the same way as before, but instead of just using image, now I have a left bracket and a right bracket again to represent that it's a template. And this is doing exactly what it did before, except uint8 type is passed as a template value, and it's going to create an image with pixels of uint8 type. So notice that previously it was just embedded inside the implementation of image. Now I am asking for a implementation of image, or an image object that is has a pixel type of uint8 type, and it's passed as a parameter. So I'm creating it at compile time. So when I'm compiling it, it's going to create me an image class with that particular type of pixel. But if I wanted to, I could go later on and create another image, and that image has a different pixel type, in this case double. So it's not just using grayscale values. You could say have more elaborate values, not just between 0 and 255, but real numbered values as the pixel values. And you could take, for example, so this is the previous pixels array from image. The image was uint8, and it's taking the difference between two pixels and storing it in this new pixels array, which is also just a two-dimensional array of colors, but the new colors are doubles. The old colors were numbers from 0 to 255. So as you can see, it's creating a new image, and the new image is a transform of the old image, but it's also stored using doubles rather than uint8. So this lets you express a little bit more fine-grained grayscale colors. So in this case, what it's doing here is, if you look at this code, the first thing it does is it loads up an image, which is grayscale. It shows that image. It draws two lines. These are also grayscale images, just in white. So it draws two lines onto the image, and then it shows that. And then it creates a new image with a different type of double, and it transforms the old image using this transform shown here in order to create an image that is the difference between a pixel and neighboring pixels. So let me just show you how this is run. It's run in exactly the same way. So I'll remove generic is the name of the binary it creates, and we have a makefile. And as you can see, the makefile is running G++7, which has some more advanced features. So this is then saying I want to run it in C++ mode, and it creates a output generic binary. There's a bunch of files to load up the PNG file, and there's a main file which I just showed you, and then the image generic.hpp, which I also showed you, which contains the template version of the image class. And if I run generic, I have to give it a file name. So I'm going to give it a PNG file. As you can see, the first thing it does is it loads up a grayscale image. And then when I click on the image, it will draw two lines. As you can see here, there's two lines that are colored white. And then it creates a totally new image with a double type, which involves differences between the neighboring pixels. And you can see it's kind of a good approximation of edge detection there. So that went by a little fast, so let me just show you here. That's kind of the double image, what that looks like. It's constructed out of the grayscale image, but it has a little bit more information. As you can see, the difference is it's kind of a very poor man's version of an edge detection algorithm that you might do. It's kind of computer vision 101, finding the edges in the image. Okay, so let's look at a slightly more advanced version of how to use these class templates. And this is for a function called normalize, which you've implemented before. And the idea is you are defining this function normalize for an image of a certain type, but when it receives a max element here, that max element may be of a different type. So for example, this type U, capital U, could be not just uint8 type. So it could not, maybe it's not grayscale, but you want to renormalize the image so that the output is a double, for example. So as you can see here, we have defined two templates. The two templates have two different types, capital T and capital U. We've defined the function normalize for the image of type T. So this is the image that currently has the pixels of this type T. And what you're going to do is create a new image with the output type capital U. And as soon as I call normalize with some variable, we know what the type is. So as soon as I know that I've called normalize with a particular variable, let's say a double, then I know that I'm going to return an image over where the pixels are doubles. And this function is defined for image with, let's say, grayscale uint8 underscore t as capital T, right? So as soon as I pass a function, call this function normalize with a double, I know that I'm going to return a double. And this is exactly what's happening here is I don't need to know what the output type is. It's just a generic capital U, and I create an output image of that type. And I fill it up with the normalized value. So it's going to have the same implementation of normalize that you had, which is you find the min and the max, and then you rescale the values so that the min and the max become the darkest and the brightest values in this new image. But when it returns it, it could return an image of a different pixel type. So the pixels could actually carry more information because what you're doing in renormalizing is maybe using more of the scale. And so the output type can be different from the input type. So this is a good time to pause and say that for Lab 10, you actually do not need to use any templates at all. I think you can solve all of the tasks in Lab 10 without using templates. So this is mainly for your benefit as you go forward and you want to implement other stuff in C++ after Compute 127. You'll find that templates are quite useful. And in fact, what I'm going to show you next is not even possible in the version of G++ installed in the CC Linux machines at the moment. They might upgrade them in the future, but as of today, which is July 2017, the CC Linux labs do not have the more advanced version of the GCC compiler that can do what I'm about to show you next. So all of this stuff is pretty old school. I mean, templates have been around for quite a long time in C++ now. But as you can see here, I'm defining this normalize function. There's a lot of stuff to type in, like you need a template for T, a template for U. You need to figure out what the image type, return type would be. And this is the image type for the base image, which I'm manipulating. So in modern C++, it's especially after the changes introduced in C++ 14, a lot of this typing has been replaced with a different operator, which actually does some amount of type inference for you. So basically it tries to figure out what the type is by analyzing your function. And if you return something of a certain type, you don't need to actually provide the return type. So here's what the new function would look like. So this is the same normalized function. It's exactly the same, but using C++ 14 sort of capabilities. So you can see that the return type is auto, and the input is also auto. So it says when you write auto, it says ask the compiler to figure out what the type is, and it does its best job trying to figure out what the type is. So in this case, for example, I'm creating an image. The image is using a template just like I used before, and I don't really know what the type of max_u is because it's auto, right? So what this is saying is find out the type of max_u, and this new image is of that type. So declare type is, it's a little bit like the size of operator, except in this case not giving the size, it's giving you the type, the inferred type of this variable max_u, and then creates a new image. And this is the same variable output as before. And so when I return this variable output, that's when C++ compiler, the C++ compiler would say, aha, I know what this normalize returns. It returns an image which is of the type that I got as a parameter as input to this function normalize. So for example, if I passed in a double, like, you know, a value that's a double type, so I don't know, maybe it was 12.34 or something like that, That's the input to normalize, and that's what you want to get out of it. Then it will say, I see that maxu is of type double. I'm going to create a new image of type double of this variable name output, and then I'm going to return output in this function. When I do return, is going to infer the type, and in the end all the code is exactly the same as you would get when you had the previous normalize function with the two templates, except here you don't have to actually type out the template. So the temptation is to just put auto everywhere, and many times that will work, but then when it doesn't work, you need to know what C++ is doing in order to figure out what's going wrong. So this is just a brief introduction to type inference in modern C++. And a lot of modern C++ will look like this rather than using a lot of explicit template types like I showed you before. So this is again something that's good for you to know. It's not something we expect you to know within Compute 127, but if you go and program more in C++, this is the kind of stuff you need to be aware of to do modern C++ programming. The focus of the course was to teach you basic skills rather than teach you the latest and greatest sort of things in C++, because the basic fundamentals are the same no matter what sort of version of C++ you're using. You still need to know about types, and you need to figure out you need to know even more about types to figure out what's happening in these type inference situations where you're using auto all over the place. So hopefully the course has given you that fundamental knowledge you need to understand all the different extensions in C, C++, and other languages that have been derived from C and C++. There's lots of languages like Go, there's Rust, there's many languages which are modern, which are sort of essentially spin-offs of C and C++. By taking this course, Compute 127, we are hoping that you can have the skill to pick up any of those languages and be able to program in them. So I've created a version of this image header file with the image class, which uses the auto sort of type inference capability of more modern C++. So this is the function I just showed you. You don't really have to read everything in there. So when I make auto, the main thing I wanted to point out is that you have to add this flag to the compiler to G++ that says that you're using C++ 14. In G++, it's not enabled by default because it's considered new, and so if you want to use it, you have to say I want to use the version of C++ that corresponds to the C++ 14 standard. And then when you run it, it runs as before. Give it a file name. So it's doing exactly the same, but it's doing all of this type inference at compile time. Sorry. So that's another attractive property of C++, is even though it's doing all of these very sophisticated type inference things, it happens at compile time. At the runtime, it runs as fast as C would. So you don't lose any performance. Okay, so 90% of the time when you're debugging a function or a program in C or C++, what you're going to do is, so let's say that you are trying to debug this C++ program. There's some bug here somewhere. The best thing to do is to put in a print statement, and you can analyze whether your understanding of the algorithm matches what is required, right? So you can use print statements to figure out what is going wrong with your program. Sometimes print statements also help you figure out whether control is reaching some part of the program at all, because you might think it's reaching there, but it's actually not getting there, and it's crashing somewhere way ahead, and your bug was actually somewhere else. So print statements are kind of the main workhorse in debugging. The other thing you can do to debug your program is to write lots of test cases that expose bugs in your functions. So you write a function with a bug in it, you can pass it different values, try to see whether the output is correct. So this covers 90% of the cases. In the 10% of the cases where there's a very tricky bug, you can actually fall back to a debugger. And so I'm going to compile this using the makefile, and it's calling G++ to create the binary. The binary is called generic. That's the name of the binary, and it takes an image file as an input. So I'm going to use a debugger to show you what a debugger does. And when the more advanced cases where you're really stuck and print statements or test cases are not helping, then using a debugger can really save you. GDB is one such debugger. There are many debuggers out there for the Clang compiler framework. So the GDB stands for GNU debugger, which is part of the GCC compiler collection. The Clang compiler collection comes with something called LLDB, which is the debugger in that compiler framework. There are many very good debuggers, especially the Visual Studio debugger is an excellent one, especially for C++. I'm going to show you GDB. So GDB takes the binary, and it loads up the binary and then lets you manipulate the binary, run it, and even though it's a binary file, it is compiled in such a way so when I use a -g option, it actually stores enough information in the binary that lets GDB actually read the source file and show you where in the source file it is. So I'll show you with an example. So it's generic, takes one argument, command line argument, which is the name of the file, the image file. So I'm going to run GDB, and I'm going to say that the program takes arguments, and this is the binary file. So when I load it, it sort of shows you a lot of different information. I'm just going to clear the screen so that it's nice and clean. And what you can do straight up is sort of list the main function. So the main function might call other functions and so on, and you can debug any number of source files using the debugger. So one thing you can do is you can simply run the program, or you can say run the program up to a certain point, and that's called a breakpoint in a debugger. So if I want to list starting, so let's say that I was interested in line number 31. So this is the line that I'm interested in. I want the debugger to run the program and stop when it reaches line 31. So I would give it the name of the file. So in order to set a debugger, so I know that I want to stop at line 31, so I'm going to clear the screen. I'm going to do main generic.cpp, and I'm going to stop at line number 31. So if I do now, when I type in run, it's going to run the program, and it's going to stop when it reaches that breakpoint. So when I run it, it runs as normal. It loads up the PNG file, shows it to me. It draws those two lines like we saw before. And at this point, it's going to create a new file, right? So what happens now is we will go back to the debugger. It says thread 2 hit breakpoint 1. So if I do, so it shows me, in fact, the source code line that I'm at. So it says I'm at line 31. I'm actually I'm going to execute this line. So I stopped as I did that. So when I do a step, it goes to the next line. So it's executing the program one line at a time. So it makes it easy for me to debug. and I step again. So notice it was in a nested for loop, so it goes to the outer for loop, and now, sorry, the inside for loop, and now it's back to this breakpoint. So let me just clear the screen and I do a list. So it's the breakpoint is on this line. So I want to figure out what's wrong with my program, and I can use the debugger to actually inspect these values. So I can say, what is x? So x has a value 2 right now. What is y? Well, y is a value 1. Here I'm doing x minus 1. So I can do what is print of x minus 1? Well, that's going to be value 2. So this image.pixels over here is going to have, well, 1 here and 1 here. So what is image.pixels 1, 1? Oh, I see. Is that, so you can look at this value and say, is that the value I wanted? And then I'm going to subtract this, this image.pixel is yx. So notice that x is a value 2, so let's look at x2, and those two have the same value, so it's going to subtract it, get a 0. So let's print out what is in dx.pixels 1, 2. So you can see that it's a 0, so it's working as we expected. So this gives you a good power to inspect variables, and so debuggers are very useful in running up to a certain point, figuring out what the values of the variables are. Is definitely useful in many cases where simple print statements or test cases are not working. The temptation is to load up the debugger for every simple crash in your program. And that might actually prevent you from trying to reason about your program as a whole. So sometimes you get into a debugging frenzy where you keep trying to look for the bug, and the debugger is not helping you. That's because the problem is not in the debugger, the problem is in your brain. You haven't written the program correctly, right? So that's what you're trying to figure out. The debugger can only help you if you're actually thinking about the structure of your program and whether the algorithm is right or wrong. The debugger cannot magically fix your bugs for you. It just gives you some tools to help you do that. So the debugger can also, so if you look at image.pixels, you can see it can show you that it's a pointer. I can dereference the pointer inside the debugger, and so it's pretty powerful. So it's going to show you a lot of information, and with great power, comes great responsibility. So you got to make sure that you're not just wasting time in the debugger, and then you get frustrated because you haven't found the bug yet. You should step back and look at your code and debug it logically first before you get into sort of putting breakpoints and doing all the stuff I just showed you without actually getting to the bottom of the bug, right? So there is such a thing as playing with a debugger. It's a lot of fun, but it may not solve your bug because you have to think about it rather than just use the debugger to print out values. You can figure that out. I think combining the debugger with all of the other strategies is really the way to go. So if once you are especially dealing with a lot of unfamiliar code, sometimes the debugger can be helpful in understanding that code as well. All right, well, good luck with Lab 10.